Hey everyone, this is going to be the first part in a series about deriving certain theorems. And the first theorem that we're going to go over is the divergence theorem. This is a very useful theorem, has a lot of applications. So the best place to start is if we take a look at a cube. And basically what we're going to want to do is begin by calculating the surface flux of some vector function f through the surfaces of this cube. And since it's a cube, then we have all three coordinates of this vector function are going to be separated out quite nicely. So if we just take a look at the x direction, then we can begin there. So first we're going to have S1, and we're going to have the force dot S1, and then we're going to also have the surface flux through S2, surface 2. And since surface 1 is out oriented in the negative direction, where N1 is pointing in the negative direction, that's going to make that surface integral negative. So we have S1 evaluated at A, and S2 is evaluated at B. And this is going to be in the first principal direction, or the x direction. But if we take a look at these surfaces, then we can see that they actually have the same bounds in the y and the z directions. So if we were to say integrate this surface, it would have the same bounds. So really these surface integrals have the same bounds, and they can be interchanged. So S1 is equal to S2. So we can bring both of these expressions under one integral of just S, the surface here. And we're going to have F1 evaluated at B minus F1 evaluated at A. So if you take a look at this, then this is actually the definition that is given by the fundamental theorem of calculus. So that's actually going to be the derivative of F1 in the x1 direction from A to B, integrated from A to B. And we still leave all of that inside of our surface integral. And then when we look at that, then we can see that actually that is going to make this a volume. So we're actually integrating this derivative over a volume. And the same results can be obtained in the second and third directions using the same method. So then what we end up with is that the surface integral of this function f, this vector function, is equal to the volume integral of this volume that has this surface in the three directions. So if we write in index notation, then we just have dfi dxi, which is actually del dot f, which is the gradient of f. So this is the result that we're interested in. We want to have the surface integral of some vector function f dot the surface is equal to a volume integral of del dot f. This is useful because now we've transformed a surface integral into a volume integral. And there are going to be times when we're going to want to use this going in either direction. But, this is only for a cube, so it has a little bit of a limited application. So to broaden the range of this theorem, then let's take a look at two cubes together. So if we try to take the surface integral of these two cubes separately and then add them together, then let's see what happens. So I've got the surface integral of volume 1 plus the surface integral of volume 2. And let's again look at it in the x direction. So I'm going to have negative f1 evaluated at A plus f1 evaluated at B over the surface, and that's going to be for volume 1. And then for volume 2, I'm going to have negative f1 evaluated at B plus f1 evaluated at C, and that's going to be for volume 2. So now you can see that there's two f1 terms evaluated at B. They're underlined, and they're actually going to cancel out because one's positive and one is negative. So now we have f1 evaluated at A plus f1 evaluated at C. And again, you can use the fundamental theorem of calculus to turn this into a volume integral. So what we've shown is that the surface integral of these two cubes next to each other added together is going to be equal to the surface integral of the larger shape that consists of the volume of both cubes, because these adjoining faces are actually going to cancel each other out. And then we can continue to use the divergence theorem so that del dot f of the entire volume is equal to that, which would also mean that del dot f of volume 1 plus del dot f of volume 2 would be equal to del dot f of the entire volume. So if we can do that for two cubes, then really we can do it for any number of cubes. So to extend this theorem to a more general approach, we're going to actually take an infinite number of cubes so that we can make any kind of shape that we want. We can even make smooth curved surfaces because we can use an infinite number of cubes, so we can make the surface as smooth as we like by using an infinite number of cubes. So then you can extend this theorem to say that the surface integral through an infinite number of cubes would be equal to the surface integral of the entire volume that those cubes represent. So then we can say that we can draw our volume, as just this sort of arbitrary blob, which is kind of the tradition, so that this theorem can apply to any shape at all, which is more useful than just a cube. So the shape can be anything that we want it to be. So we have the surface integral of f dot ds is equal to the volume integral of del dot f dv. And here I am crossing the v because I'm going to use regular v for velocity, and we want to save the other letters for other things. This theorem also applies to scalar functions, except that the volume integral would just be del f, not del dot f. And this also applies to tensors. So here I'm defining this volume as a fixed volume. Sometimes you'll see people define the volume as being a function of time, but that seems rather strange to me and also unnecessary, because we're going to be able to do everything that we need to do with a fixed volume. So this would represent some fixed volume of some imaginary line that we've drawn in space around, and then we can evaluate vector functions through this boundary.